A very good evening to one and all, and I welcome all of you in another interesting session of the sixth lecture workshop on transdisciplinary areas of research and teaching by Shanti Swarup Bhatnagar Awardees. And today we have with us Professor Debdeep Mukhopadhyay from Department of Computer Science and Engineering, IIT Kharagpur, and he'll be talking to us on topic cryptographic engineering, journey from theory to practice. So before inviting Professor Debdeep to deliver his talk, I would like to briefly introduce him to the attendees. So he's currently a professor at the Department of Computer Science and Engineering, IIT Kharagpur, and where he initiated the Secured Embedded Architecture Laboratory, the name SEAL, with a focus on hardware security. He had worked as visiting scientist at NTU Singapore, visiting associate professor at NYU Shanghai, an assistant professor at IIT Madras, and a visiting researcher at NYU London School of Engineering, US. He holds a PhD, MS, and B.Tech from IIT Kharagpur, and his books include Fault Tolerant Architectures for Cryptography and Hardware Security from Springer, Cryptography and Network Security by McGraw-Hills, Hardware Security Design Threats and Safeguards from CRC Press, and Timing Channels in Cryptography from Springer. He has written more than 250 papers in peer-reviewed conferences and journals and collaborated with several Indian foreign organizations. Professor Mukhopadhyay is the recipient of the prestigious Shanti Swarup Bhatnagar Award for the year 2021 for Science and Technology and is a fellow of the Indian National Academy of Engineers. He was awarded the DST Swarnajayanti Fellowship in the year 2015-16 and a Data Security Council of India Award for Cybersecurity Education, ASEM-DUO Fellowship, INSA Young Scientist Award, INAE Young Engineer Award, Associateship of the Indian Academy of Sciences. He was awarded the Outstanding Young Faculty Fellowship from IIT Kharagpur and the Techno-Inventor Best PhD Award from the Indian Semiconductor Association. He has recently incubated a startup on hardware security, ESP Pvt Limited, at IIT Kharagpur, and is a senior member of IEEE and ACM. With these words, I now invite Professor Devi to kindly share his screen to deliver his talk.
So first of all, I would like to say thank you to Professor Saxena for this kind introduction, and also to all the organizers and also to all the attendees for coming to this session. So as mentioned, I would like to kind of again repeat that this title of my talk would be on hardware security in the modern world, from things to cloud. And in this, I will try to also emphasize on the journey that I had been a part of. So here I would like to kind of mention that my research largely deals with the topic of what we call as hardware security, which tries to bridge the gap between theory and practice. So this is the classic overview on how security works. So if you think of like usually any security algorithm or any cryptographic algorithm, which is nothing but the art of or the science of like making things like confidential and like trustworthy and ensuring the integrity of communications and so on, while also ensuring the availability of information when it is required. So while cryptography has been like quite age-old and classic, I mean, I would like to mention that nowadays, right, it has become ubiquitous. So knowingly or unknowingly, we are all using some form of cryptographic algorithm. Okay, and so here is a very classic illustration of how or the endpoints of a cryptographic system. So imagine that you have got a sender and receiver, and they are communicating with each other. So think of like Alice and Bob, two friends who are communicating. They are using an encryption algorithm and a decryption algorithm. Both of them are known to the public. That means everybody knows about how these algorithms are made. Okay, what the adversary, or maybe you can think of the eavesdropper who is shown here as Mallory, does not know is a secret key. Okay, and therefore the objective of an attacker is to obtain the value of the key. But the cryptographic algorithms, or the theory of cryptographic algorithms, typically try to ensure that it is very, very difficult, to some extent infeasible, by a practical attacker to obtain the value of the message or maybe the secret key from the communication. So, but we all know that cryptographic theory, because of its limitations and because of the absence of theory for what is happening in the real world, they fail. And the mathematically strong ciphers have been shown to, be failing in the real world. So one of the reasons why they fail is because of some information sources which are not always taken care of by, or it is not possible also sometimes to take care of by the developers of these theoretical constructions. Okay, because in the real world, your cryptographic system, so it could be your credit card or maybe your mobile device, the crypto in your mobile device is continuously leaking information. Okay, and these leaking informations or these leaked information are not only the inputs and the outputs that are being exchanged, but are actually the various kinds of information sources which we call as side channels. Okay, so side channels could be the power consumption of the device, could be the electromagnetic radiation of your device, could be the behavior under faults, and so on other things. Actually, it could be the sound that is created by your computing system that is continuously revealing some information on the computations. Okay, because of which, the entire theory of crypto algorithms can fail if they are not properly implemented. So this journey of designing secure cryptographic systems can be nicely probably understood by this example. So it says that suppose I make a theoretical statement, like it says that suppose there is a mathematical group on which I define some computations where there are certain hardness notions. So in computer science terminologies, we call them as notions of hardness, because these problems are very hard because in a sense like people have tried but not really been able to solve. So one of them is what is called a discrete log problem. But when you want to really work as a practitioner, you need to implement them by actual instances. So one of the instances could be, say, using an elliptic curve cryptography, which is a very popular and next generation, or so you can say that the current day de facto standard of using public key cryptography, which is often used in our web browsers and other applications that wherein we are using some form of cryptographic techniques. But then what can be observed here is that there can be many attacks that can break real world elliptic curve without really solving this hardness notion, or which we call as discrete log problem, or in the context of elliptic curve, which we call as elliptic curve discrete log problem, or ECDLP. And the reason could be because we implement often these systems in a manner that they probably can have nice variations maybe in the timing required for the computation, and that can often happen because of the choice of the curves, which are usually defined for which are defined without thinking about these potential side channel leakages. Okay, and therefore this theory or to practice translation is very important, and that largely defines my line of research. Okay, so therefore I would like to mention here that in theory and practice are same, but in practice they are really not. And this defines this journey from theory to practice to build more and more secure systems. So in order to work in this direction, we set up this lab, which we call a secure lab. So we started to work on various topics. We started to work initially on VLSI of crypto systems, like when you want to really implement this crypto on your hardware devices. We started to look at formal verification for finite field circuits. And then we try to look into side channel analysis, which I will try to talk about in my presentation. We are recently working on post-quantum crypto. On the passing, I would like to mention that because of the advent of quantum computers, many of these public key cryptographic systems are often broken. And therefore, there is a new generation of crypto algorithms which are coming up, which are called as post-quantum crypto. And they're extremely complex. And they really pose, additional design challenges, which we'll try to kind of address in this line of research. Another important line of work is what are called as microarchitectural attacks, which also has been, one of our, I would say, mainstay of our research. And in this line of research, as we'll see briefly in our presentation, is that when you're implementing a crypto on your standard computing systems, like your desktops or maybe your laptops, the underlying computer architecture is largely tuned towards performance. And because of this, there are several caveats or artifacts which can potentially leak information. And that is what we try to study in this line of work. Another important area that we need to kind of work on is what are called as Trojans, which means like there could be some malicious or surreptitious modifications in your circuit, which can be fired at very important times. And they are extremely hard to detect and hard to these are against modifications. So I will briefly be talking about what are called as physically unclonable functions, which are very emerging, new piece of hardware security primitives, which can provide unique fingerprints to the devices. And this can be very or potentially very useful in the context of securing the Internet of Things, where we know that we are trying to connect billions of devices together, and therefore the security or the authentication and trust across the devices is extremely crucial. And this brings us to IoT security. We are also concerned about machine learning, being used for both attacks and defenses, and of course, like cyber physical systems. So, largely started to get this advanced encryption standard. So roughly around 2001, when I started to work on this domain after my undergraduate degree, I found out that the AES, or the advanced encryption standard, was the most popular crypto algorithm which was getting proposed at that time. So this falls under the category of certain ciphers which are called as block ciphers. And 20 years, it still stands strong, which means it's really well designed by two Belgian cryptographers. And AES is what you take any system around, right, you'll find that there is AES probably working underneath. And therefore, right, this motivates us to look at the real security of AES when they're deployed on actual systems. Okay, right? That is not only the theoretical security, but also the real practical security in your various solutions which are around us. So as I mentioned, that strong cryptographic algorithms are just the beginning. So if I take my maybe credit card, which is secured using such kind of algorithm like AES, and if there is a normal input-output exchange, the mathematics is fine. I mean, it probably will be able to secure our secret key. But if you imagine that the device on which you are swiping your card is also observing the power consumption, then apparently, right, it can really leak the secret key. And there are algorithms which can really leak the secret key in a very straightforward manner. Luckily, our credit cards are now secured because of the research, right, around the world, which tries to protect against such kind of attack vectors. So let us try to take a little bit closer look at such kind of efforts. So here is an example of the AES algorithm which is working, and there is somebody who is also observing the power consumption of the device. So note that it is not only the power consumption of the part of the chip which is performing the AES, but it is actually the total power that the device is consuming. So somebody can also try to, take maybe a probe and observe the electromagnetic radiations. So, but interestingly, what it shows is that you will find out that there are some distinct variations on the power line. And certain things are quite evident here. For example, you will find in this trace, which is shown on the left of the slide, that there are, say, 10 jumps inside this trace. And if you study the AES algorithm, you will find that there are 10 rounds of operation. So that is quite evident from the power trace. Okay. If you zoom into one of the rounds, which is shown on the right, you will also find out variations. So these variations are occurring because of the underlying operation. So if the AES algorithm, there are fundamentally different types of operations, like there are certain things which are called as S boxes, which are nonlinear transformations. There are certain linear transformations. All of them have got a different effect on the power consumption. So this variation is what are called as simple power analysis of the traces. Now there is an even powerful, or like a stronger form of adversary, which are called as differential power analysis, which means that the power consumption of the device actually depends upon the underlying data. So that means, like, because of the power consumption, you are really revealing the internal data on which you are processing. And this was shown by this famous paper in Crypto in 1999 by Paul Kocher and his team, which fundamentally led to a very I would say, like a very famous company, which essentially shows us how to perform differential power attacks and essentially recover the secret key of such kind of standard algorithms. So here is a snapshot of in our laboratory, right? You can perform these attacks and can recover a 128-bit secret key in quite a small amount of time. So in this case, you require to do, say, 15,000 AES operations to reveal the entire secret key, which is a 128-bit secret key. Now you may probably it will probably be, I would like to emphasize this at this point, that if you do not do such kind of side channel attack, then if you take the AES crypto system with a 128-bit secret key, there are 2 to the power of 128 possible keys, right? And that is probably more than the number of particles in this universe. So a brute force search will not work, but a side channel attack, because of its nature or because of its efficiency, can recover the secret key in a very, very practical manner. So here is a very top level illustration of how the AES cryptanalysis works. And I will not really go into the details, but rather just give a very top level understanding of how these attacks work. So you can observe that there are different inputs here, for example, which are shown here as plain text, which is the input that you're giving to your crypto algorithm. And then what you try to do is, remember that it has got a 128-bit key, which means there are 16 bytes, and every byte is an 8-bit of information. So you want to recover that key. That means you want to recover the entire 128-bit key, but you do not want to recover the key at once, but rather you try to develop a technique which is based on divide and conquer, which means if there are 16 bytes in the key, I will recover each of the keys in a byte by byte fashion. So let us think without loss of generality that I want to observe the first byte of the key. Okay, the first byte of the key, which means the first 8 bits of the key, can take 256 possible values. So these are shown here as the key hypothesis. So these are all my key hypotheses. And I start to understand, I need to understand which of the key hypotheses that key. So therefore, I take these 256 choices and I go ahead and compute partial, like maybe the first round of the crypto algorithm, but just only on one part of the plain text. And then I come to somewhere which is called as the intermediate data, or the hypothetical intermediate data. And then I apply what is called as a powered model. So the powered model essentially are, like certain things which we see in our VLSI discourses, which tells us that how the power consumption of the device would depend upon the underlying data. Okay, so and there are various powered models. Simplistic powered models like Hamming weight also works quite nice, which means that if I take a byte, I'll just make a count of the number of ones inside the byte. Okay, so if I apply that, I will be able to kind of map this hypothetical byte value to like a Hamming weight value, which will probably vary between 0 to 8. And then this is what I call as a hypothetical power. Okay, and likewise, also while this encryption is taking place, I also observe the actual power traces, which are called as bits. Okay, so this is my real power trace, and likewise, I have also observed what is called as the hypothetical power trace. Okay, and now note that hypothetical power traces was observed based upon the key hypothesis that you did, right? That means essentially I made this was my first key hypothesis, and this is my second hypothesis, and this is my 256 key hypothesis. So the hypothetical powers that I'm observing are dependent upon the corresponding key hypothesis that you have made. Okay, so now what I try to do is probably apply some kind of statistical techniques, which could be, like in a very simplistic sense, just a correlation computation, apparently like return key, which gives me the highest correlation between the real power trace and the hypothetical power trace. So it turns out this simplistic technique, right, essentially works quite nicely. Of course, like it requires more refinement to handle noise and other kind of variations, but in a very simplest, in a very top level manner, this is the, like fundamental behind the attack. So now what it is that you can and so in order to look into, like more closely, in a more close manner how this works, we also try to look at other attack vectors. So let me talk about a faulty perspective of looking at these crypto attacks. So if you take a crypto system and you can target it to various kinds of attack vectors, like this is what is called as fault attacks, or falls under the class of what attacks we are called as fault analysis. And you try to create perturbations through which you can create some kind of faults inside the circuit. Okay, so maybe I will shoot in a laser gun or maybe an EM pulse, and that will probably modify one of the internal bits in a random manner. I do not really need to know what it will modify, but it will make like some modification to the internal data. So now the question is, right, the first question is that can you really do it practically? And the second question is, can you exploit it using your analysis? Okay. So in order to practically demonstrate it, there are several kind of attack vectors, or you can see here instruments that we essentially or laboratory setups that we have tried to make to demonstrate that such faults are possible. In particularly, these are also possible purely from the software mechanisms. Okay, for example, if you see your computing system, there is something which is called the DRAM, which is the memory chip, as we know, right? Now, these DRAM devices also have got some reliability issues, which are called as row hammers. So what we tried in one of our prior work is try to kind of access the memory very fast so that it doesn't get time to get refreshed. And because of this, there are certain 0 to 1 or 1 to 0 migrations that happen. So what we showed in one of our prior work is that using such faults, you can recover the entire 2048-bit RSA key, which is often used in so rather than going into like that attack description, what I will be talking about today is I will try to restrict onto AES and try to understand how faults can be used to reveal information in the context of block ciphers. So the idea wise, this is how it works. If you take a plain text and what you obtain the normal fault-free cipher text, but in this attack setting, you try to create a fault injection, which will give you a faulty cipher, and then you analyze it to get the secret key. So now the question is, right, how does this attack work? So what you do is you create as I said, that when you are creating these perturbations, there are some internal faults that are being created. Maybe there is a random fault that has got created. And now when the ciphering happens, this fault passes through various transformations. Okay. Interestingly, because of the way the ciphers have been constructed, you will find out that after a point, the faults start to show some kind of interrelationships. For example, here you can see this is the state of the AES algorithm, which has got 16 bytes. That means you can count that there are 16 bytes, and each of them are bytes, which means the total number of states are 128 bits, as I said, in the context of AES. But interestingly, if you observe the first column here in this square array, you will find that there are certain bytes which are maybe double than the other, or maybe there are certain bytes which are equal to the other, which means that there are some interrelationships across the faults. If you go down further, you will probably get some more relationships. So now what the attacker tries to do is, from the output of the cipher, it tries to guess the key and then go back and check that whether these relationships are being satisfied. And then you only keep those keys which satisfies these relationships. So what you essentially do is build an attack in a similar manner. And in one of our prior work, we showed that only one single fault is required to break the AES key. That means if AES normally, right, has got, say, 128-bit secrets, which means that there are 2 to the power of 128 possible values. Using a single shot, you can reduce the key size to only 256 values. Okay. And if you get a double shot, you can uniquely retrieve the key. So this attack essentially has been very fundamental because it shows that a single fault essentially is enough to compromise your crypto systems, which are running not only on your embedded systems like credit cards, smart cards, but also on your present day things like your normal computing system. So it could be your Intel machine or your SGX machines and so on. And people have shown several follow-up works of how to utilize this attack algorithm to kind of complement it with practical experiments of injecting the fault and recovering the secret key. So that means that it is extremely important to secure them and to test your designs against such kind of attack vectors. So we also try to develop like suitable countermeasures against them. But it turns out that to design countermeasures are not easy. So in one of our very recent works, we showed that even if you have a countermeasure, so there is a very popular countermeasure for crypto, which tries to ensure that nothing inside the chip is operating on your actual data. So what they do is, suppose you have got a data, say X, you try to kind of, break your data into 2 parts. So this is what we call as secret sharing. That means if there is an internal data, say X, you try to break it up into components. So let me call one component as X1 and the other component as X2, so that X is nothing but the XOR of X1 and X2. So that implies, so this is what is called as sharing. So you take the data X and you share it into 2 components. So now if you want to recover X, you need both X1 and both X2. So that makes the side channel attacks or fault attacks more difficult. But in one of our recent works, we showed that even if you have such kind of sharing and countermeasures and so on, one can essentially take a very standard implementation. So these are what are called as TI or threshold implementations. And when you inject the fault, then you can just observe when you're injecting the faults inside the registers, you're storing these intermediate values, which we call often as masks. And then just observe a template, and the template essentially is nothing but that whether the fault that you are creating is getting exposed to the output or not. That means whether the fault injected is really like showing up in the output. That means whether it is getting absorbed by some internal computation or whether it is showing up in your output, which is often evident from by just input. And then once you get this template, then you can develop a methodology through which you can recover the corresponding internal states, and hence you can recover the secret key. So therefore, it is not very, I would say, naive to develop such kind of countermeasures. You need a better engineering, understanding, testing to really ensure that your designs are protected against such kind of attack vectors. So that motivates us to look at various countermeasure techniques. And we also try to work in this direction of trying to understand that whether your designs are secured against such kind of fault attack vectors. For example, in this case, what you can do is one of the experiments that we are trying right now, and we have some initial works on that, where we try to show that if you have got a protected cipher, you try to do a black box fault, different fault instances, and then observe the output and try to see that whether the observables are differentiable or not. So the idea is that if the faults essentially are showing up in the output, then that means it is leaking information. Okay, so we try to develop a black box methodology. So because it is very important to test your designs, and often industrial counterparts are not very enthusiastic about opening up their design IPs, but still in a black box methodology, you should be able to detect that whether there is any possibility of the internal faults. It is also important to like sanitize the hardware that you are designing. For example, India is one of the primary, although we are great in terms of exporting software, our hardware designs are often like imported, and therefore there is always a question about whether they can be subjected to such kind of attack vectors. So it is important therefore to develop methodologies through which you can develop like a black box framework to detect such kind of attack vulnerabilities. So we also have a startup, as was mentioned, and we call that as ESP. So we have tried to package all these tools, and we call these as ESP Anvesha. So before I start, here is a quick, like demonstration or a tour of our side channel setup. Hope it works. fault injection was trying to show you that because of internal that was getting changed. So that was showing that how the EM or the electromagnetic radiation is able to change the internal bytes and create the fault. So continuing further, we also, the other area that we are related area that we are also looking at is what are called as microarchitecture attacks, which tries to, address the gap between security and practice, or rather I would say the gap between hardware and software. So many of us have probably heard about this attack vector, which is called as Spectre and Meltdown, which opened up a very glaring weakness in our modern day computing systems. So one of the important hardware, or rather I would say like this, the design principles of computer architecture is what are called as speculative execution, which means in a very simple sense that if there is an instruction, say, let us take an example, say I want to compute, say, A divided by B, or the computer wants to compute A divided by B, but then the division is not allowed when B is 0. You cannot divide by 0. But the computer, what it tries to do is it tries to go ahead, and once it finds out that there is a problem, it tries to unroll. So our computing systems, and there are many other occurrences like branches and so on, which tries to handle which tries to work using this technique of speculation, which really improves upon performance. However, it has been found out that because of in this process, when you are doing your computation, the information can leak through various interesting hardware resources. One of them is what is called as the cache memory. Okay, and it has been found out that these attacks are so powerful that it can help the attacker to obtain passwords, your personal photos, emails, instant messages, and even critical business documents. Okay, the question is like, how can you fix them? So fixing them is very, very difficult. So if you want to fix them, it will require a patch that will result in a major performance hit. But more interestingly, you have to go back 20 years of your evolution of your computing system. So that motivates us to look at these kind of attack vectors. And interestingly, your Spectre is an attack which also used a finding from our group. And I would like to mention here that it is emphasize here that it is very important to mind this gap. So the holistic approach is needed in order to build secure systems, because by understanding and modeling the proper architecture-aware leakages. So the question is, right, how do we really build or ensure that our microarchitecture? So there are different kind of hardware artifacts. For example, the branch prediction algorithms, the hyper-threading, memory technology, and cache architectures, and so on, which can leak information to knowingly or unknowingly. Okay. So therefore, right, and it is important to mention that the underlying hardware, if it is not properly designed, such kind of attacks will work irrespective of the best crypto algorithm that you're using. So let me try to emphasize on the cache memory, which has been one of our primary thrusts of research. So we have tried to look into the cache memory, and we know that the reasons why we have the cache memory is to bridge the memory wall between the microprocessor, which is very fast, but the memory, which has really not been so fast in terms of its evolution. But then the very definition of cache memory implies that if you get your data in the cache, what we call as cache hit, then access time should be less. But if you don't get data in the cache, then access time should be more. So that means there is a timing difference. And the question is, can that timing difference reveal information? So let me give a very top level description of how the attack works. And there is a very popular form of attack, which is called as cache timing attack, which can work even in a remote setting, which means imagine there is a remote attacker and there is a remote server which is running software, and you send a packet, get back the information, but while you get it, you also observe the timing for encryption. Okay, so the question is, can this timing reveal information about the secret? So let us try to understand this by this famous attack proposed by Bernstein, which says that if you take the AES, as I mentioned, right? It's a 16-byte input, which means there are 128 bytes. So what you do is you fix one of the bytes, and the other 15 bytes, you vary them at random. And likewise, you observe the corresponding timing for encryption, you observe the average timing, and you plot this in a graph. Okay, and you repeat the value of, or you give a different value of this first byte, and you keep on doing it for 256 possible values. And in this process, you will get a timing characteristic. So the question is, how does this timing characteristic get information about the secret key? Very interestingly, you will find that if you repeat this experiment with two different keys, maybe one of them is 0 and the other one is the actual key, then the timing characteristic is pretty similar in both of them. You can observe this. However, you will find out that, for example, if you observe this bundle over here, and maybe, and this bundle, you will find out that there is a shift. Okay, and this shift can be picked up by maybe a correlation or similar kind of statistical distance. And it is very interesting that this shift corresponds to the secret key. So that means that you can really, obtain this timing information. It can reveal information about the secret key. So why does this timing vary? So if you take a standard software implementation of AES, maybe an OpenASL implementation of AES, which is often implemented using a 4 kilobyte table lookups because the software designers wanted to make it fast, you will find out that the number of cache misses is directly proportional to the difference of the timing. And it turns out that in context to AES, there is a nice distribution of the cache misses, which reveals, which creates these timing differences, which can be exploited by the adversary. So there was a popular myth in literature which says that probably this will not work if you implement using a smaller table. So that means if you implement the AES engine or the AES cipher using smaller table, maybe a 256 byte table, then because of the fact that the table is small, after a few rounds of encryption, the entire table gets loaded into the cache, and after this you get constantly cache hits. So since you do not get that nice distribution in the cache miss, probably the timing will be constant. So it will probably a constant timing implementation, and therefore will not reveal information to the attacker. However, so this was a popular belief, but still possible under such settings. So interestingly, we tried to attack like a cipher with small SBox implementation, and we showed that one can recover the complete 128-bit key in something like around 300 seconds. Interestingly, the attack works on Pentium 4, Intel Atom, Xeon Core 2 server, which were like popular computing systems at that point of time while doing this research, but this attack failed on older generation computers. So why does it happen? So in order to investigate this, we found out that there are many techniques in our present-day computing systems which helps to kind of reduce the time and enhance performance, and they essentially are the real culprits of such kind of leakages. So we tried to look at one of the important I would say hardware, what we call as hardware prefetchers. So hardware prefetchers are architectural artifacts which essentially helps you to load data into the cache by observing your access pattern. For example, like if you find out that there is a say arithmetic progression in your access pattern, then it will probably go and make some early accesses and put them into the cache. So the next time when you access them, you find out the data is already available in the cache. So what we try to model is these prefetching techniques and try to understand what is the influence of this on the overall timing pattern. So why does it matter? Is because the prefetching essentially depends upon your internal data. I mean, the data that you essentially start your encryptions with, and therefore potentially can have a bearance on the overall timing. So we try to model this information leakage by using some information theoretic techniques, which for the sake of time, I will not get into details, but we were very accurately able to predict the timing variations, which happens on present day systems, and show that how or what is the responsibility of hardware prefetchers on such kind of leakages. Interestingly, using these models, we also were able to develop, I would say, prefetching methods, which are, completely silent to such kind of leakages. So this is a paper that we published in, the Journal of Cryptology, which is state-of-the-art ISCR or International Association of Cryptologic Research journal. So we try to, not only stop at cache memory, but also look at other hardware, techniques, which are, for example, one of the very popular artifacts is what are called as branch predictors. Our present-day computing systems also have got these kind of artifacts, which continuously tries to understand the branch patterns, and from there essentially makes decisions, which helps to reduce certain penalties. But then we found out that if you take an Intel machine, right, and you do not know anything about the prefetcher, and therefore we made a very simplistic guess on the prefetcher. So one of the guesses that we made was assume that it kind of replace it by a simple 2-bit predictor or a 3-bit predictor, and we found out that a very simplistic model was able to predict the the branch patterns, and from there we showed that how one can recover RSA keys on Intel platforms. So Hello.
Hello.
Yeah, so there was a glitch. So I
Yes,
hope
yes,
I'm
sure.
back, right? Okay.
Okay.
Yeah. So continuing, right? I mean, these kind of attack vectors, we also can apply it on various countermeasures. And you will find out that in one of our recent works in transactional computers, we showed that even like such kind of branch predators can break legacy codes on cryptographic libraries, and which has got countermeasures. Okay, and for the sake of time, I will not go into details, but just like redirect to some of you who are interested and show that you can recover like the secret keys of standard cards like carve 1174, which is often used for digital signatures and so on, using these branch predictor leakages. Interestingly, right, we try to use certain monitoring tools which are called as performance counters. And one of the outcome of our research is that we showed that such kind of leakages can, I mean, the exposure of performance counters has got security threats. And nowadays, if you want to access performance counters, you need root privilege, which shows that, like people have been concerned about such kind of attack vectors.
Professor Debdeep, there is a certain block on your presentation. I think there are 2 blocks which I can see that's actually hiding the content of the slide on the top as well as on the right hand side.
Okay.
There is a bar, a box which is appearing.
Is it still there?
Yeah, the right one has gone, but the top one is still there. Maybe if you can put it in the slideshow. I mean, earlier it was not there.
Okay, so let me do one thing. I'll just unshare and maybe share once.
Sure.
Okay, is it still there?
Yeah, that's still there.
Okay. So
yeah, now it's not there.
Okay, good. So hopefully it's fine, right?
Yes, now it's fine. Sorry.
No, that's fine. Yeah. So thanks so much for pointing out. And yeah, so
Yeah, we can't hear you.
there is a glitch.
Oh, that toolbar is back now.
I don't know what's happening. Anyway, so maybe security attack. Okay, so
Okay.
So yeah, I hope it works. So basically, like I would rather like switch my topic. So I would like to briefly talk about somewhat on identifying what are called as physically unclonable functions, which are very promising primitives for securing in the context of Internet of Things. We know that Internet of Things are very promising in the sense like it connects billions of devices together. Unfortunately, like IoTs do not have any protection against attacks, and therefore it is extremely crucial to secure them against various attack vectors. But at the same time, many of these IoT devices are very low cost, and therefore we need low cost mechanisms for protecting them, even side channels. So in this context, we try to look at paths. And before I go into that, I mean, I would like to kind of explain why I said that IoTs do not have any secrets. So this is a famous example to illustrate that, and we also tried that in our laboratory. So Philips essentially used to sell what are called as Philips Hue lights, which are smart bulbs through which you can communicate with, or you can whitelist to a switch. If you're whitelisted, then you can control and command them. Of course, you do not want your neighbors to control and command, but unfortunately, many of these authentication mechanisms are extremely flawed. So we also tried to do an investigation, and we found out that the way they do the authentication, right, essentially is very naive. That means like what they do is they generate a random number, and then they essentially transfer them on the cleared, which you can like catch by some kind of eavesdropping tool. And therefore, right, one can easily masquerade as the other and create havoc and control and command these bulbs. So that means if you had a fight with your neighbor, then you will find lights turned off. So the question is that why are they not secured? So one of the main things is cost, and therefore you need to like put your classical crypto into this context and ensure that they are really secure. So this brings in the context of puffs, which we call as physically untunable functions. So what are puffs? So puffs are basically like not really mathematical functions, but I would say like circuits, which if you implement them on different devices, and if you apply the same challenge to these devices, then the responses that you get from these devices are statistically independent. So as you can see here, there is one challenge that is applied to all these devices, but the responses that you get from all these devices are unpredictable. So they need to be unique and at the same time unpredictable. They need to be kind of independent of each other. So interestingly, puffs, I mean, if you can design such puffs, then the hope is that you can really reduce the cost and you can raise the security and so on. However, there are some design challenges or like that also needs to be mitigated because of the definition of puffs. We really clone the puff because of the fact that every device has got a unique fingerprint. You cannot also use the puff at the receiver end. That means like if you, for example, imagine that there are two devices which are communicating and one of them have the puff, the other one cannot have the copy of the puff because there is no clone of the puff. So what you can do is you can store challenge response or the input and the output of the puff and store it in that verifying device. And once you essentially send the challenge, you get the response. You can, of course, verify it by matching challenge response table, but then you cannot use that challenge response again. Okay. And this essentially tells us that there is a natural, I would say, like limitation, because you need to store the challenge response at the verifying end, which essentially limits various kind of industrial applications. So this essentially motivated us to look at, like techniques or developing techniques of how you can really implement puffs without really storing the challenge responses on the table. So in one of our works, we try to develop a methodology by combining public key cryptography and coming up with a method which you actually can implement, through which you can actually implement IoT subsystems embedded with puffs, and you can rule out attacks. For this particular illustration, we show here one very popular IoT application, which are the video surveillance cameras, and show first of all how you can inject stale data and you can kind of completely subvert the security policing that you are doing. But with puffs, you such kind of meet in the middle attack or like attack vectors. So this is something that we are also doing in collaboration with Wipro, and there is an article which talks about this collaboration and also possible technology transfer. So here is a very quick like demonstration of the puff circuit, and it works. basically shows that that one can prevent such kind of fake, like intermediate efforts, because of the fact that the adversary doesn't have the actual puff device to respond to the. So I would like to kind of, like probably I'm running out of time. So I'll just very briefly talk about the final frontier that we are trying to work on, which is on the other end of, which is also called as cloud. So we all know that we have got several data critical which are being continuously pumped into the cloud. So this brings us several questions like privacy concerns, how do you manage the data? And the question is about co-resilient attackers and how do you perform analytics? So one of the things that people tells is probably that, or you will probably think of, is that let us encrypt and keep the data onto the cloud. But if you adapt any encryption, and you cannot perform any processing on that, like you cannot perform analytics, you cannot do search. So this motivates us to look at techniques or develop techniques through which you can also do search while the data is also encrypted. Of course, you do not want to do something which our popular, like vendors are doing, where they write that, like they do secured encryption or secure search, but they silently tell that they decrypt it, which means your data is getting revealed to the corresponding server, which is allowing you the search to perform search. So what we rather, and there are like several techniques we are being developed around the world, starting from what we call as fully homomorphic encryption, which are very secure but at the same time not very efficient. On the other hand, we have techniques which are more efficient but they are not secure. Our path is to take a middle path, which is try to develop what are called as searchable symmetric encryption techniques, or SSE, and try to nicely balance between like your security leakages, but at the same time make it amenable to search. So in one of our recent efforts, we try to develop a methodology through which you can perform such kind of searches. And I will not go into the details of the technique, but I'll just talk about the result. So the result tells us that you are able to now perform such kind of searches. Like suppose you want to perform a search, which is, let me take an example of, say, I've got my emails, and suppose imagine that my emails are encrypted and kept onto the cloud. And I want to, while they are encrypted, I want to, like make a query that is where the recipient is Alice and the sender is Bob, and say the IP address is such and such, and the subject is crypto. So such kind of queries, we call them as conjunctive searches. So on encrypted data with 60 GB of data, I mean, we show that our query response time is less than 1 second. And at the same time, it prevents against various attack vectors, which essentially were plugging the present day technique. So this is something that we are trying to build. And maybe, like I'll just quickly conclude with a quick demonstration on that. So here is a search engine that we built, and the data is encrypted, and still we'll how we can perform the search. Search that you are writing, say AES and SSE. You want to search for files which essentially have these keywords, and all these files are encrypted. So that means the server also does not learn anything about your query values. So these are the corresponding files which you can download and then decrypt. Server does not learn anything about the content or anything about the keywords. So this is a system that we are trying to build to ensure privacy enable search. So we are also trying to see that how we can make them accelerated using various hardware methodologies, and see whether FPGA clusters can be used to build more competitive systems. So before I stop, here are a few future directions that we are working on. And I say that hardware, India is a largely importer of hardware devices. So it's always a pressing concern that whether our hardware is trustworthy. In this context, we are trying to develop some intrusive methods using very advanced imaging. Here is a MEMS chip. And suppose I'm curious that what is inside the MEMS chip. So this MEMS chip you can see is even smaller than this coin. So interestingly, recently, right, there were some results where showed that how some of the like hardware or other computing platforms developed by a company in US was hampered or was kind of polluted by some small devices which were built in China, and people were really concerned in the sense that those devices can be used for communicating information, and they're extremely hard to catch because you can think of your printed circuit boards where they are modified, where they are inside the IC, difficult to be detected. So what we are trying to develop is right now we are trying to work on imaging methods using image processing as well as like maybe machine learning techniques. So you can see here is now we can detect that inside this chip there is an antenna, and potentially we can try to categorize them in a proper manner. The other direction that we are also trying to work on is what is called as fully homomorphic encryption, which is kind of a holy grail in computing. The idea is kind of similar to what I said in symmetric searchable encryption, but the thing is that here I want to do arbitrary computation. So this can really open up applications where privacy is important, and at the same time computing on private information is important, but at the same time the present state says that it is very, very inefficient. So what we are trying to see is whether we can design and implement them in a leakage resilient manner, and at the same time get end-to-end secure systems. Another looming threat is from quantum computers, and therefore the encryptions based are actually post-quantum resistant. So therefore it probably motivates us to look into such systems. So with this, I would like to conclude these words that hardware security is very crucial, but interestingly, it also requires expertise in various domains like security, embedded systems, VLSI, architecture, computer networks, and nowadays even ML, because you need to understand the attack surfaces properly. You need to kind of, and there are several heterogeneous attack surfaces starting from thin to pervasive clouds, and they can offer different kind of attack surfaces from side channels, the inability to support costly ciphering operations, like various kinds of attack vectors, and therefore we need to develop novel tools. That is what we are trying to, and we are trying to develop constantly new hardware primitives for an end-to-end security, because what we have to keep in mind that a chain is no stronger than its weakest link, and they have to develop an expertise which kind of encompasses various various endpoints, and therefore the nice part is that if you are working in any domain in computing, you will probably find some very important role in this context. So here are some textbooks. If some of you are interested, probably you can take a look. Is on hardware security, timing attacks, which I tried to talk about briefly in context to cache attacks, fault attacks, and there is also an online NPTEL course on hardware security, which is actually currently running. And with this, I would like to say thank you for your attention. With these words, it says that every computation leaks. It's a slight adaptation of this famous statement, which says every contact leaks. But in our context, every computation that your systems are doing is actually revealing information. So it makes sense to work to secure such systems. Thank you.
Sure. Thank you very much, Professor Debdeep, for enlightening all the students and faculty and research scholars about the, I'll say, the evolution of this particular area, which I think will be not only relevant for the students, but in terms of the industrial application of the theory, whatever they study, that will be of great help and great use to it. Sure. So there are a few questions. I'll take up one by one. Sure. I think the first one is related to that. Can IoT-based appliance be protected? And if yes, then how?
Well, I mean, of course, like, I mean, IoT, I mean, the security of IoT has been evolving. I mean, initially we were more, I would say, concerned about the, the applications that you can build around IoT, and that is also emerging. And the difficulty of, bringing in security in IoT is because there are no clear definitions of protocols. There are so many heterogeneous protocols that are, working with each other. So, so the question is, people have been to see that the authentication protocols that you develop for IoT follow standard methodologies, like essentially follow the standard cryptographic protocols and techniques. But often people like that they are costly, but therefore there is one, I would say, like there are one line of research which really tries to ensure that say the OpenASL or the security algorithms are really implemented in a very resource constant setting so that they can be like imbibed into our IoT solutions. And on the other hand, there has been also works where people have tried to do something which I tried to hint at, where you are using unconventional methodologies, like maybe like physically unclonable functions. And in this context, you will probably see that there are commercial companies which are actually now like creating like puff solutions which are based on what are called as SRAM puffs. So SRAM puffs means like if you take the SRAMs and when you boot up, you will find out that there are unique fingerprints, like 0-1 patterns, which are very unique to that device, that can help you as a source of identity, which are being used in the context of securing IoTs. So in a nutshell, I would say that it is still like an emerging field, because IoTs itself are emerging, but people are trying like to adopt classical methods to secure them, as well as trying to develop unconventional methods to secure such communications. Yep.
Okay, thank you. There are 2-3 more questions. I'll take up one by one. So the first one is, can the dual mode puff be also cloned by machine learning?
Can you please repeat the question?
Well, can the dual mode puff be also cloned by machine learning?
Okay, that's a very good question. Actually, the idea is that when you have got a puff, the puff, as I mentioned, right, if you give, there are different types of puffs. For example, the puff that I SRAM puffs, it typically do not expose their responses. So in such kind of settings, you do not bother about machine learning largely. Okay, but in other contexts where you're exposing the responses, then definitely machine learning is important, and people have shown that most of these puffs, which are strong puffs, are actually vulnerable to machine learning techniques. And therefore, this is a constant, I would say, pursuit of puff designers to ensure that the designs are secured against machine learning. So on one hand, while it seems quite challenging to completely rule out machine learning techniques, what we try to do is rather make machine learning more and more difficult, in the same time, and make them more and more costly. And in this context, right, you will find out in recent literature, there are various puff designs. Like in particular, from our group, we developed a puff which we call as multiplexer puff, which is built on like standard delay-based puffs, but at the same time, they are more robust and secured against machine learning methods. But at the same time, there are also other groups which are doing them. For example, there is a puff which is called as interpost puff. Then there is a puff recently which is proposed as LP puff, which is really more resistant. Then there are some other variants of puffs which are called as analog puffs, typically, which people have also shown to be more resistant against machine learning techniques. But having said that, I mean, do they really theoretically edge out machine learning? I don't think so. I think that most of these designs are vulnerable to machine learning in a theoretical sense. But what we essentially try to do is make machine learning very costly. So in one of our recent papers in ICCAD in 2020, you will find that there is a tool that we propose, which is called as PuffG, where we try to analyze using a language framework that once you take a puff, you have a new puff design, you can write in that language, and the tool will automatically do the complexity of a good from the learnability point of view. Okay, and that way we are trying to build like complexity classes into which you can categorize the puffs. So in a very simple sense, I mean, I would say that if you have got a strong puff design, then the best way to understand that how much resistant it is to machine learning is to really actually perform the machine learning. So you can, try to, apply various machine learning techniques. Of course, you have to, study how the machine learnings are being adapted for such kind of designs. But once you, gather that, then to actually perform the ML and get a quantification on the number of inputs that you, but if that number is really high, maybe you need, say 650 million inputs to model a puff, which is of say 64-bit dimension, then you can pretty much live with that risk. In an IoT setting, I think that is pretty good security.
Sure, I'll take up the last question, although it's a bit different from the talk which you have shared. First part is what is a configurable tri-state PUF? That's part one of the question. And the second is the lightweight cryptography is a novel diversion from conventional cryptography that targets IoT platform due to resource constraints. Your comments.
Yeah, I mean, of course, like lightweight cryptography, I will rather take the second part of the question first. So lightweight cryptography is a different discourse in itself, right? You try to develop dedicated ciphers, but large cryptographies are like usually restricted to block ciphers, and nowadays we call them as authenticated ciphers or authenticated encryptions. But the point is, right, I mean, that's not the entire world, right? You also would like to like develop protocols using them, and we all know that symmetric keys cannot give you the end-to-end, cannot give you all the components of the protocols. Definitely it's an important piece. Like if you are developing a lightweight cryptographic cipher, then that will definitely have its own applications in the context to resource constraint designs, and that is the whole reason why lightweight cryptography have been studied and have been but I think you also need to complement it with other pieces, and that is exactly what I try to kind of stress at, like developing protocols and like cryptographic protocols which are slightly unconventional in the sense that they do not really do away with security, but at the same time they are also efficient. Yeah. Sure. So I think I missed out the first question.
Yeah, I'll just repeat that part. What is configurable tri-state PUFs?
I'm not exactly sure about the exact part of the design, but I think if I recollect, I think like, of course, like I can understand that, like tri-state will probably have to do something with the tri-state buffers, but at the same time, I'm not exactly, aware of this design technique.
Sure. Thank you. So thank you very much, Professor Debdeep, for sparing your valuable time and addressing all the students and the faculty members. And I also would like to thank the attendees for asking very inquisitive questions and enriching this whole seminar. Yeah. Thank you.
Thank you all. Thank you for like your questions late in the day and still staying
sure. Yeah. Thank you.
Thank you.
Thank you very much, sir. Okay. Bye-bye.